Okay. So I think we can start. Okay, thank you. So good morning, everyone. I'm Fabio Dell'Acqua from the University of Pavia in Italy, and I share with Mrs. Amanda Regan the pleasure to chair this first morning session. And this session will be on a mix of trending and hot topics regarding the latest trends in Earth observation, spaceborne Earth observation. I will leave the ground to Amanda for introducing herself and introducing the first speaker. Thank you, Amanda.
Good morning, everybody. My name is Amanda Regan. I'm the head of the Invest office in the Phi Lab, and I'm also the program manager for the Investing in Industrial Innovation program. With that, I'd like to start this session. I'd like to invite Marco Esposito to the podium. He's our keynote speaker this morning. Now, Marco is actually the program manager of remote sensing at CoSign in Leiden in the Netherlands. And he got his PhD in aerospace engineering and managed the development of the ERB-2 camera, which makes 3D movies on the ISS. He's also got a wealth of information in optical systems. And he's currently the chapter leader for a high-level textbook for airborne measurements and the leader of an expert working group for turbulent measurements in how do you pronounce this, the UFAR?
Yeah, UFAR.
Okay, UFAR consortium. He's going to talk today about HyperScout-1, which actually I know very well because this is the second activity in the InCubed portfolio. So, Marco, with that, you have 20 minutes. Go.
Thank you very much. About the textbook, actually, the text is a bit old. It's already published, so it's readily available for reading. So thank you, Amanda, for the introduction. And indeed, I'm going to talk about, I'm very happy, first of all, to be the keynote speaker today, very honored. And so today I'm going to tell you a little bit what happened in the last few years, so where we are now with unlocking hyperspectral and thermal sensing and artificial intelligence on small satellites. So we did quite some, you will see, developments to get where we are here. So first, one slide on the company. CoSign is a Dutch company in the Netherlands, so very close to ESTEC. We deal with quite a lot of remote sensing development of products and technologies. So we are organized in 3 units: high energy optics for astrophysics missions, inspection systems for terrestrial application, and remote sensing for small payloads, in this case for Earth observation, but also for planetary science. What we're talking about goes into this remote sensing group, and we have 5 lines, of which the hyperspectral part is the core of today's presentation. So we started, I think it was something like 5 years ago, with an idea of developing a very compact hyperspectral system that for the first time would be able to unlock hyperspectral on small satellites. So it was the beginning of a bit of the hype of the CubeSat, of nanosat for Earth observation. But we come, as I said before, from an history of planetary science development. So we were really used to make compact payloads for planetary science. So we looked with ESA, the science department, in many cases. And HyperScout is a bit the result of many years of breadboarding and developing in the lab of miniaturized spectral imagers. So HyperScout is a 1.5 liters imaging system with 45 bands in the visible and infrared, and only with 1.5 kilos is actually able to deliver a very wide swath. And this means with a few items you will be able to have a very high revisit time. That was a bit the concept at the beginning. So let's make very wide, let's make the pixel. We didn't care about high resolution because in this case we talked about high spectral resolution. That is the core message also I want to pass. So in this case we are not, let's say, dealing with the geospatial information, it's more spectral information, even though in a slightly larger pixel. And so one of the problems we tackled from the start was, in general, hyperspectral is a technique that inherently produces quite a lot of data. So we are talking about terabytes per orbit. So how we can deal already on big sats with this kind of amount of data, but on small sat, how we can make sure that these data do not get locked into the spacecraft, actually, how we can use them, because downloading was, at least 5 years ago, not an option. I see nowadays there are quite some technologies that will help, and actually are improving, and this will make downloading more data possible, but still is a bottleneck. So we worked hardly with different consortium. You will see a little bit also the history to try to do the full processing on board. So starting from raw data and go through the full processing line and get to geophysical parameters on board. This means actually avoiding the download at all. That was a bit the very challenging target we posed to ourselves. And with this, enabling also early warning systems. So we looked, you will see an application like flooding, fire hazard, fire monitoring, all kind of, let's say, application where you need a reaction time, timeliness very, very short. So the only way was to try to, let's say, get a compromise between the onboard processing in terms of hardware, so how fast we can actually run algorithm without crashing, without getting problems in orbit, and how we can shortcut the actual algorithms in order to do that. So we, let's say, launched the first HyperScout in February 2018. We have been working with it, let's say, during this period. And what we managed to demonstrate so far was to be able to construct the hypercube, so the spectral data cube in orbit. This was proven, let's say, at the end of last year. And so this is a payload that is actually commercially available. Thanks to Incubed, we improved the payload. You will see in which way. I have to say, commercially is also a success because there are, let's say, one commercial item will fly at the end of the year with a US company, and there are a few in the pipeline contracts to be signed. So the HyperScout-2, that is an evolution of this first model, where the veneer hyperspectral system was improved by adding also 4 channels in thermal infrared. That is one of the very nice highlights. So together with, let's say, the reflectivity, the albedo measurements with very high, let's say, for this kind of system, spectral resolution, we're talking about 50 nanometers bandwidth. So we are able to couple co-registered by heart, so really with the one front-end telescope, means you get the hyperspectral and the thermal sensing in the same optical system. This means that you get co-registered data by heart, so you don't need to care about it in terms of post-processing. And this enables much more applications. So knowing the reflectance of a target and also the thermal behavior, so the temperature, this makes possible to do any kind of energy balance, evapotranspiration, but also many more applications. And what also we added in this payload is a way of improving our processing system. So already on board HyperScout-1, there is a CPU. We have also a GPU. We have also an FPGA. But on HyperScout-2, we added on top of these 3 items also a VPU, so a vision processing system. And this, so we added a lot of efficiency. So already before, it was possible to do quite a lot of processing. With this, we add efficiency. So it's specialized for inference, so for artificial intelligence, and the efficiency indeed for inference is very high. We are talking of order of magnitude better. And so we are going to try with HyperScout-2 that is ready for launch. So will be is already integrated into a satellite and is part of the F-Sat-1 mission. That is, let's say, the first of the Earth Observation Directorate as a small sat mission, and includes all this. All this was done also in a very short time. It was another challenge, a bit to prove that this kind of demonstration can be done in a quickly manner, so that we can spot very quickly in orbit what are the let's say the problems to tackle in the next round, and not, let's say, doing the full modeling on ground that was used for bigger systems that need a very high reliability. So here we accept a bit of risk, let's say. And it's very nice that ESA also starts doing this kind of exercises because it opens a lot of new developments possible. Just quickly a recap of the, let's say, comparison between the 2 models in terms of specification. So you see, let's say, a very, I said, wide field of view. So one of the challenges was to make this telescope, is a TMA, so a 3-meter astigmat, based on freeform technologies, was one of the first, let's say, of this category. And freeform is actually enabling this miniaturization. So we are able to have a very wide field. So we're talking about 31 degrees means something like 320 kilometers wood. From 540 kilometers altitude. And again, this is a very small form factor. We also looked a lot how to make this telescope alignable during manufacturing. So to eliminate all the overhead in the lab to align this actually 4 meters. And so this is also one of a big achievement together with ESA to make sure this can be done quickly. And this means for constellation, for orders of high numbers, makes life and time, let's say, very short. And so the main highlights, as I said, are the very big focal plane. So you see 12 megapixel, even though we use 8 megapixel on the veneer. And as I said, 45 bands with 15, 16 nanometers bandwidth in the visible near infrared, and 4 bands in the thermal infrared. So the bands in thermal infrared were selected based on existing systems, so Landsat, MOVDIS, Sentinel-3, in order to also in the future be able to cross-calibrate, to leverage all conventional satellites that actually have a much more stable and calibrated data. This means we want to use, let's say, the Copernicus, let's say the conventional satellites, also from NASA, as a reference points for many applications. You will see there are quite some activities ongoing on this. Yeah, a quick outlook of the optical layout. You see the TMA plus a folding mirror, and we were really challenged by making the thermal channel part of it. So we had to really make in a very small volume a full relay in order to improve, to enhance the numerical aperture of the system and indeed enable the thermal part. So let's say the very nice technology that we integrated is this VPU. So it's a Media 2 system from Intel. And we integrated in this system together with our partners, Obotica, and you will see also in a presentation later from ESA, the first demonstration for intelligence on this chip has been already developed, so we'll also exercise this in orbit, and this is together with the Synergize and the University of Pisa. You will see in the end a full list of companies that are working in the different projects. So this is a very compact, ultra low power, so it means with 1.5 watts you can actually use 12 shapes that are specialized, let's say, processors, and these make, as I said, the inference very, very efficient. And there are, let's say, things I think to say about the limitation for hyperspectral is very demanding. So these chips at the moment are very good for multispectral. So also our hyperspectral was downgraded to multispectral in order to try out. But I think in the roadmap there are ways of using these chips in parallel and in series, kind of a network, so that we can improve also or we can exploit fully the hyperspectral capability of our system. So just to show you a little bit, has an outcome of the first mission that is in orbit. So I will show just a few data, and then I will show you later how we get to real spectral data cube. So these are frame images. So each image contains a full spectral evolution along track. These are data collected between, let's say, September and January, February this year. So here it is over Australia. What you see here, it's indeed, so California. So you have very wide swath again. So you can really appreciate in this case, was about 220 kilometers. We did quite some campaigns for calibration. So you will see some calibration site, usually, let's say, very commonly used by Earth observation activities. So this is over Algeria. We use these sites for geometrical calibration. Over deserts, this is the Libya 4, very, very also famous, let's say, for who deals with calibration in Libya. You see, these are two interesting scenes over, let's say, one is Syria, and the other one is Morocco, where we are trying to elaborate our agricultural algorithm. So together with our partners, in this case TU Delft, University of Delft, that has already a lot of projects in these plots. You will see later some tubes and some agricultural fields that also shows that with this kind of resolution, you can actually do applications at agricultural level, at plot level. And water quality, this is next challenge for us. So as a company also we want to deal more with water quality. We think it's very important that we monitor this in a better way and or in a different way, complementary way to what is already possible. And we want to really focus in next years to make sure our company can contribute to this topic. But in the end, what we care about is the spectra. So all these are collected in order to build the spectral cubes and get out these kind of curves. This is the plot over California and shows, let's say, a few behaviors like the red edge that is typical for vegetation. So you really see the knee, and you see that the nice part is that you can also do with the multispectral, but with the spectral you can actually sample the actual knee. So there are few parameters that before was not possible to achieve, like the PRI, the photosynthetic reflectance index, that is very, very wanted by the community, and with this kind of application system you can already produce now. And in the end, let's say the first demonstration, as I said, over this data set was to build the cube in orbit. And this is the baseline now for any other application. So for HyperScout-2, as I said, the application is actually very, very broad application range. Opens up a lot of different things. So that's a bit of the problem of HyperSpectral. So a lot of things can be done, and so people get a bit, let me say, lost into this because it's really, really broad. So from our side, we will focus on these ones, especially with HyperScout-2. The plan is to collect quite a lot of data. For HyperScout-1 was quite limited, I have to say. We downloaded only something like 13 acquisitions, and you will see what are the constraints in the next slides. But with HyperScout-2, the hope, let's say, at the moment, there is a good hope that we can get down quite a lot of data. And therefore, we are also look for partnerships in order to look at this data, so to organize projects together and really perhaps deal with the single application with different companies. So we want to also use this to do more networking and have more partnerships in order to be more successful in commercially towards, let's say, the world. So we want to team up as much as possible. So you will see later how you can contact me. Of course, people know me, but there is also a website where you can apply for applications together. But this is the range. So we look at, as I said, the flooding, change detection. That's very common, but with spectral sensing, I think you can add another component. So you can look at changes that are not possible to detect with normal imaging within multispectral. So you can see more changes in the spectral domain. And urban islands, fire, but fire is interesting because already with the veneer, with HyperScout-1, we can do fire hazard, so not monitoring, but really giving a risk map of where fire can actually happen. And now with HyperScout-2, with the thermal part, we can actually do the, let's say, prevention, and then we can do also the monitoring and detection. So it's a very complete chain. And as I said, water quality, this is something we're already looking with some acquisition. We also have some collaboration with the US and Canadian companies and try to really see with this small system how accurate we can be, especially with the algae bloom and the cyanobacteria in this kind of applications. And let's say least but not last, so evapotranspiration, you see here a very nice plot that I was, let's say, dealing with many years ago with airborne systems, but this really tells you how you can detect evapotranspiration means how healthy are plants or vegetation in general compared, you see here, let's say trees that are the very red spot. This is a latent flux that is calculated from this energy balance. You see how the trees actually evapotranspirate and how the soil instead is very flat. But what is the final goal? Final goal is to enable a system can, let's say this is simulations with one HyperScout, with one system. So the idea is to, with one system, do multiple applications even in the same orbit. So this was a planning we had for the first HyperScout, a trial that we will still try. We didn't manage to implement in terms of money and time, but it's still in the plan to organize, let's say, a set of acquisition and processing real time and delivering of this information per site to the users. And all these were selected because there are projects on ground where we can get truth. Measurements on ground. But if you can scale up this with more satellites, with more HyperScouts, for example, we did some simulation with the 12 or 15, you can actually start to get sub-daily revisit. Means you can deliver, if you're able to process quickly this information, even, let's say, we had some simulation hourly, let's say, information for all this kind of application in near real time. So it becomes really a different game and a different way of approaching the same problems. So it can be, again, complementary to more accurate measurements with institutional satellites. But we think can add really a lot to timeliness and to reaction time and to different aspects. Change detection, already with HyperScout-1, we were simulating with the actual system, and this is next step to be done in orbit. So how to get from 1.2 gigabytes size of one data cube to something like few megabytes by only detecting the changes, that changes can be spectral or spatial, and downloading only the parts that actually changed, and discard all the rest that stays the same orbit to orbit. This makes, let's say, really the hyperspectral part powerful, and it's actually, if it's done in this way, possible also with very small platforms, with low power consumption. And the challenge, this was based on a CPU and this kind of numbers, but now we are going to see with this VPU what actually can be added. Again, with this VPU, I think we cannot do hyperspectral yet, but multispectral is already something we can try and see how much more efficient it is compared to normal CPU or GPU. This is the implementation of F-Sat-1, so that is HyperScout-2 complemented with this VPU system. So you see that we have already, as I said, onboard data handling, CPU, GPU-based, FPGA, and now we added this media tool that you see in the top, in the bottom right. And this is something now is experimental, so it means we have to load in a batched way the data, and we can run experiments. And next step is to actually integrate in the full chain. And most likely the idea is to put it really at the edge, so really at the output of the sensor, where you can do inference in a very quick way compared to previously planned. And this, as I said, is for us is a platform that we want to exploit with many parties. So it's now, let's say, already in the satellite, will be in space most likely beginning of next year because of the problem, or let's say the delay we got with the launch, but everything is ready to go. And yeah, already now we want to get started talking to different companies and see what are the applications that you would like to do and how we can organize projects in order to develop these algorithms and to upload your algorithm on board. So at the moment we have you will see, as I said in the next presentation from ESA, first results from this, we are doing a cloud detection as a first application, but we really want to open on many applications. We would like to exploit this platform that is a lab in space that actually can be used for experimental research and make sure that algorithms are not only validated on ground, but can be in a cheap way validated in orbit directly. So this is the chain at the moment we are offering, where let's say the first part up to pre-processing is done basically by our infrastructure, and the inference part is done by any party. At the moment you will see University of Pisa, Synergize helped in the first application, and but let's say can be any one of you basically. I think it is 1 minute left, so I want to show a few data cubes. So what you see here, this orange box, is a typical SWOT of HyperScout. You see in the bottom, let's say, the 300 kilometers, what you see here. The problem with the small sat is, in my view, still the downlink. I hear around that actually this can be overcome nowadays, but I have my own doubts. So still I think we have to do a lot for onboard to actually make this happen. So for HyperScout-1, what you see, for example, is half of the frame is something we can download in, let's say, in a few days if we go for a kind of multispectral, so not all the bands. If you want to go really hyperspectral, then we have really to select a little band. What you see here is an optical flow method that we developed as part of the F-Sat-1 project to actually make this data cube quicker than before, and even is a relative data cube, so we have all the bands co-registered, but are not georeferenced, let's say, pixel by pixel. But at least we can have the pixel spectra, let's say, per pixel, sorry for them. And this enables, in a fast way, let's say, any other application. Still, we have also the traditional way of doing the full rotation metrics to get the position per pixel, but this, we believe, for the AI application will be much more efficient. What you see here is, for example, simulation of, this is over, I think is Nevada. So what you see here are the bands from HyperScout processed in order to simulate Sentinel-2 bands. So what you see here in this box. What you see in the bottom instead is using the 3 bands RG and near infrared to create a composite image. So here is another example. So this is in Syria, and you see again 300 watts, half of it, and this is the actual hyperspectral part we managed to download with these constraints. You see here are agricultural plots, what you see there, and so there is not reported the wavelength, but this is actually the full scan, and you see a big change after the red edge. So you see that few plots are actually reacting a lot because some are irrigated, they are not harvested yet, and some others are in a different way. So I go to conclusion. We're also running a very nice project with the P-Lab, try to cross-calibrate HyperScout with Sentinel-2 with Landsat 8, so try to make the HyperScout part compatible with other systems. And we are, for this, running airborne campaigns for doing this cross-calibration, and I want to show only, this is the interesting part we are trying to cover in order to have agricultural fields, water, and different applications covered, a very high resolution with the airborne and cross-correlate with HyperScout, with Sentinel-2, with Landsat 8. And we did all this with machine learning, try to cross-calibrate the two systems. These are a few very fresh, actually, data. I think also technical officer didn't see it. I hope he's okay with it. But these are, let's say, you see the wavelength, and this is over the Netherlands, you see the spectra, let's say, per pixel. So I conclude. Roadmap, I think perhaps is not interesting. You can talk to me, I can tell you more. The interesting part is that you can contact us, you can apply for an application on our website, and we can talk how to test your software on board the platform. We are available at the moment together with ESA and with our partners. Very quick, and then I'm done. The projects at the moment are, let's say, these ones you see. The HyperScout-1 is done with a GSTP and with that consortium. HyperScout-2 is done with Incubed and also EOP. And CloudScout Fsat-1 is done with Philab and University of Pisa Synergized as partners. Thank you very much.
Okay, unfortunately, there's no time for questions. I'd like to hand over to Fabio.
Thank you, Amanda. So thank you, Dr. Esposito. Thank you for your presentation. Let me remind the audience that in case you have any question, you can still ask them via the Slido tool. Okay, so that can make for the